You can see this, isn't it?
Yes, sir.
So your this is actually little bit, you have to your what you call understanding is required. Only I'll show you the how to construct zero sequence diagram. Later the fault thing will come, that how fault will be fault current or voltages will be computed using your symmetrical component. But the only problem is that zero sequence diagram is the major thing. Positive and negative sequence diagram are not a problem. For example, you draw that. That's why you will find that all the examples I have given, that zero sequence, right? Data and other thing will be seen later. For example, this is a generator. It is star grounded, right? This is a motor. It is also star grounded. Here there is no no ground reactance or impedance. Here also one ground reactance is there for the motor, and this is delta star grounded, and this is star grounded delta. This is a transformer. Now question is that only zero sequence diagram, what you will do, you will take a reference line, right? Look, this side is delta, this side is star, and no your what you call, and if it is your what you call that your the grounding, if any your grounding impedance or anything is there, whatever it is, right? If it is z0 is not there, then it is zero. So this side is delta, so from this is grounded, so this side no zero sequence current will flow from here to here. That's why this is open, that point P and Q it is. So P and Q from this side, generator side, is not connected, it is open, because this is delta, this is star. Had it been star grounded, and then and suppose this is grounded, then the circuit should have been from here to here, right? Anyway, so this is actually star grounded, this is delta, so this is open, and this is Z0. Here also motor case Zm0 is there, motor reactance, and here also you have one neutral grounding reactance is there, or impedance. So 3Zn we have seen earlier, this is 3Zn, and this side also it is grounded, and this side is delta, right? So this side it is connected to the reference, right? And this side is open, that is Rx point, that is this is also open because this is delta. But if you look into that, it is star grounded, and here also star grounded. So from here to here, that your current will flow, zero sequence current will flow. So this is ZT1 transformer impedance, impedance. This is also transformer impedance T2, and this is the transmission line ZL0. So this is your zero sequence diagram. So you have to see that how things are grounded, whether lines are parallel or not, or whether delta delta star star. Accordingly, you have to make the zero sequence diagram, right? Now here also forget about this parameter. Parameter will be seen later. So here also, if you look into this example, that is a parallel line, line 1, line 2. Two lines are parallel, right? And this side, your generator 1, it is star, it is grounded, and impedance is given. This is also G2, that impedance is given or reactance is given. And this is star star, both are grounded, and this is delta star, right? This calculations, other thing will be later, right? That is only thing is that per unit system, whatever has been taught, that you should keep in your mind for the third test also, that per unit system is required. So because you have to convert everything to a common base. So here also if you look into this, that you have to see this is star grounded, this is delta. So from this side, when you take the reference line, will be open, no current will be flowing. This is also star grounded, this is also star grounded, this is star grounded, this is also grounded. So all these things will be connected in series or connect to the reference line, right? Look into this, that your this side, this is generator thing is again, parameter will be computed later. This is your what you call, that is 3Zn, then generator reactance or impedance, we call impedance, right? And your this side will remain open because this is delta. Now star is grounded, here also star star grounded, here also grounded, right? So and these two lines are parallel line, line 1 line to impedance, this is line 1 line to impedance, and this is transformer impedance, this is transformer impedance, and this is generator. Two generators are there, right? And therefore this is everything is connected to the these two line in parallel. So with that, this is in series, this is in series, this is in series, and all should be connected to the reference, because this is star grounded, this is both star grounded, and this is also star grounded. For example, if this star is ungrounded, say if this star is ungrounded, then things say double up to double line things should be there, and things should have been open, and as this is star grounded, so this should have connected to here only, right? Suppose that means, suppose this is star ungrounded, then this is star grounded, then what should have been happened, that after this line it should be opened here, and from j 0.7 take a line and connect to the reference, because this side is star grounded, this is also star grounded. So he has to, one has to be, but only that zero sequence network is a problem. But you have to be very careful about this delta star star delta. The calculations, other thing we'll see later, right? So this is another one. Look at this one. Forget about the data, right? This is star grounded generator. This is actually star grounded, star grounded. All this is star grounded, but this side it is ungrounded. Motor is ungrounded. So as it is ground, it is ground, it is ground, it is ground. Up to this it is okay, but motor should not be connected. So everything is connected. These two parallel line. So this is your. It should show like this. That Q E all you have to mark all point P Q. Some marks are point A B C D E whatever it is. It is marked P Q E F. So accordingly you will draw. These two are parallel line. So all are grounded, connected, but motor is ungrounded, so it should not be connected to the reference line. It will remain open, right? Because for fault calculation, this zero sequence diagram is necessary. Suppose fault is created somewhere here, right? Then positive sequence, negative sequence, zero sequence you have to draw, and fault is created from this point. So from this point, all the references line, reference bars, you have to connect. That will be seen later, right? Similarly, here also, if you look, that your this is your this diagram. This is star grounded. This is delta star grounded. Delta star grounded. This is star ungrounded delta, and this is star grounded delta, and this is star your ungrounded generator, right? So positive sequence diagram, it is given positive, negative, and zero. Positive sequence diagram, the way you draw your conventional circuit, same thing, right? Now, negative sequence diagram, only generator source should not be there, and whatever negative sequence impedance will be there, same as it is, right? No problem. Positive sequence, as usual, the way you draw the common circuit diagram, same thing. Negative also same thing, but no sources should be there, and you have to replace those things by negative sequence, reactance, or impedance, right? Now, if you now come to the zero sequence, right? Zero sequence, if you look into this is delta, this is delta. So this is your star grounded. So what happened for this thing? This is your this is bottom line is reference one. So this is zero sequence is there. All the neutral grounded 3Zn, then generator zero sequence reactance is there, but both are delta. As both the things are delta delta. So no zero sequence current will flow. That's why this is open. This is open, right? Now, if you look into this side, that your this one, this is star grounded, star grounded. This is star grounded, but this is star ungrounded. So if you look into this is star ungrounded. This is open. This is star grounded. So it's connected to the reference line. And this side, if you see, this is star and this is ungrounded. This is delta delta. So everything will remain open. So this is also open. This is also open. Everything will remain open, right? That means this part has no contribution in the your fault current. When you see the fault studies, this side also you will find no contribution. Only contribution is here, this side, right? So that's why zero sequence has a lot of importance for computing fault current. That will be seen in the next chapter, right? So you have to practice, right? You have to practice. So what you will do now for this chapter, this 9.4, then your 9.5 and 9.6, you will draw only zero sequence diagram. That will be an assignment. 9.4, 9.5 and 9.6. This will be an assignment, right? Very simple it is. This is star grounded. This is star grounded. This is delta. This is delta. Whatever zero sequence will be there, draw from the reference line. This side should remain open. This is delta. This side will remain open. This is star grounded. So this line should be there. This line should be connected, but this side will remain open, right? The way that above example it is there. But here two generators are parallel. Two lines are in parallel, right? Similarly, here also star grounded delta. So you will draw this side will remain open. It is star grounded, star grounded, star grounded. So all these things you have to take together, connect in series, connect to the reference line. Problem is solved, right? Here also star grounded delta. So this side will remain open. Here star grounded, but this side is ungrounded. So this side it will remain open. Similarly, the star grounded delta, it should not be connected to the reference line. This should remain open, right? So you will draw this as an assignment. I'll give you your I'll tell you when you will to submit, but before returning to the campus, I think I'll request you to submit. I'll give some this thing, let me cover another chapter, then I'll tell you when you'll submit. But keep ready everything. When you'll submit every page, you will write your name and roll number, right? And your those who have regularly attended the class, perhaps you do not know, but I noted down, right? But others, those who have not attended, perhaps for them they will not get full marks. I have some data. Perhaps you will not be knowing, but I know. I'll do everything from my side, right? This is very clear, because those who are coming and this thing, even exam also, those who have just written equation and finally from the friends they have taken written the answer, for them no marks is given, only 1 mark is given. But some of you calculated everything. I have seen it. Every step, every calculation is there, and three or four for different slack bus one. I think those cases, bus one is slack bus two, bus three, bus four. I think some of you have made exact calculation, not all, but I have seen, particularly I have seen. I will not mention the name here, but I have seen it. Some of you have made exact calculation without any error up to second iterations, right? And I have seen it. So anyway, so these are the assignment, right? Very simple assignment, no calculation. Only you will draw the zero sequence diagram and put that thing. But this numericals, whatever is given here, you must practice from your offline exam, right? So now this unbalanced fault. Now, when you will consider fault, now the zero sequence concept will come here. But just see this. For example, that whenever you know that the three-phase short circuit is a severe fault. I mean, among all the type of fault, that three-phase short circuit fault, like, or what you call, it carries I mean very high large fault current, right? But although three-phase short circuit is very rare, but if it happens, that severity is more. Similarly, that if in a power plant, if there is a fault at the generator terminal, then that severity is almost same to your three-phase fault, right? That fault also very rare, but if it happens, severity is more, right? But other types of fault are, that is your single line to ground fault. Suppose you have three phases A, B, or C. Maybe line to ground fault means maybe phase A to ground, or phase B to ground, or phase C to ground. This may happen during your heavy storm or tornado. This may happen, right? And this fault, and then second fault is line to line fault. That means, suppose line to line fault, suppose A to B maybe touch together, or B to, suppose one tree is touching, sometimes one tree can touch all the three conductors, so there may be a three-phase fault, right? Otherwise, line to line fault, it may happen due to some mistake or something, right? At the time of working also, sometimes something can be touched, right? And double line to ground fault, that is very rare. There will be two line fault, simultaneously it has touched the ground, so double line to ground fault. So line to ground fault, line to line fault, and double line to ground fault. So and another fault is there, that is very rare, open conductor. Suppose some high tension line, of course, the tensile strength is very high, it will not cut so easily. But if it happens, that is called open conductor fault. That is rare, that may not happen, right? Now, single line to ground fault. So this mathematics is very simple, huh? Mathematics is very simple. Suppose the generator is there. Suppose you call three phases. This is EA, EB, EC, right? Suppose three-phase generator with neutral grounded, and your through impedance your Zn, right? So this is your EA, EB, EC, and this is your Zn. And as your what you call, suppose that fault, like single line to ground fault, at phase A, it has fault has occurred here. It is touching the ground, and fault impedance is Zf. So therefore, this voltage is Va. As the fault has occurred here in phase A, your this thing, then all the current will go through the fault, right? So other two phases current will be zero. This is from your intuition. Other phases current will be zero, IB zero, IC zero, because if fault happens, even if load is there, load current is negligible compared to the fault current. So what will be the minimum current? such that it will be fatal for human being in ampere. Anybody can tell little bit, any idea, general knowledge? Minimum, such that it can be fatal for human being. What will be the minimum current? Some idea? Do you have any idea? Tell something. Some ampere you tell. Any idea? No idea? Hmm. Nobody can tell what will be the minimum current which will be fatal for human being. No answer? No answer from anybody? What will be the factor of this thing, minimum current? That is something you tell. You are an electrical engineer. Something you tell. Ultimately, all of your goal is to get a software job, I understand, but tell something. No idea? Anyway, so come to single line to ground fault, right? It is so. This is your the other thing that IB and IB is equal to 0 and IC will be 0, and this is your Zn, right? And this current, whatever is going, IN will be equal to IA because the other two currents are 0. So if this is line to ground fault on phase A, right? And voltage is VA. VA will be IA into ZF, right? So it is because this is actually going to the ground, and other two cases, this is VB VC, but IB is 0 and IC is also 0. Now that means the condition bound, that condition for this fault, line to ground fault has occurred on phase A. IB is equal to 0, IC is equal to 0, and VA is equal to ZF into IA, right? Therefore, the symmetrical component of fault currents are that we know that your IA1, IA2, IA0. We know this from the previous chapter, right? So 1/3, 1 beta beta square, 1 beta square beta, 1 1 1. This is IA. IB is 0, IC is 0. Therefore, IB is 0, IC is 0. Therefore, IA1 is equal to IA2 is equal to IA0 is equal to 1/3 IA, right? Therefore, this equation 10.3, that is VA is equal to ZF into IA. VA is equal to VA1 plus VA2 plus VA0 is equal to ZF into IA, and this IA is equal to 3 into IA1. That's why it is 3 ZF IA, right? Now, thing is that for positive sequence diagram, first what you will do when you will do this sequence diagram, the positive sequence diagram, you know this is EA and Z1, and voltage will be across this V1, right? Then negative sequence diagram, it will be Z2 across this voltage is VA2, and this is Z0 across this voltage is VA0. Now looking at this equation, you have to make this connection. I mean, after that, how to connect this positive, negative and zero sequence your network. Looking at this equation, this is the equation available to you. VA1 plus VA2 plus VA0 is equal to 3 ZF I1. So this is 3 ZF. Look, this is connected to here, this is connected to here, and this is connected to here, right? This way the circuit is completed. So looking at this equation, you have to draw that your complete your what you call sequence network connection for single line to ground fault, right? So this is how things are connected. So accordingly, you have to connect this. I mean, first you have to draw positive sequence, then you have to draw negative sequence, then zero sequence. These three are known to you. Previously, you have seen it. But looking at this equation, you have to connect such that this equation is valid for this fault studies. So accordingly, it is connected. So this is how the zero sequence connect your connection network connection for single line to ground fault, right? For synchronous generator. Now IA1, therefore from this circuit, IA1 will be this is EA divided by Z1 plus Z2 plus Z0 plus 3Z. Very simple series circuit, right? And therefore IA is equal to 3 IA1. From here you have seen IA is equal to 3 IA1, right? All are equal. IA1 is equal to IA2 is equal to IA0. Therefore this is your IA. Similarly, under single line to ground fault, the voltage of line B to ground is this relationship we know, VB will be beta square, VB is equal to beta square VA1 plus beta VA2 plus VA0, right? So it is your VB beta square. Now this is EA, VA1 you will get EA minus Z1 Z1 IA1. Similarly VA2 you will get it, all these things, right? So all these things minus Z2 into IA2 minus Z0 into IA3 IA0. But IA1 IA2, here you have seen that your IA1 IA2 IA0 is one third IA. So here that's why it is written all IA3 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 and IA3 all are equal. So that is your VB, right? Similarly VC expression, beta VA1 beta square VA2 plus VA0, you substitute VA1 VA2 VA0 and simplify, this will be your VC, right? This is that your fault voltages during fault in your what you call phase A, right? This is for line to ground fault. Now second one is that line to line fault. So line to line fault means two phases say there is a fault. So for example, suppose B and C are short circuited. This is B and this is C are short circuited. Therefore, here in this diagram, IB direction somehow missed it. That IB is flowing from this side, right? And IC is flowing to this. So basically, IB is equal to minus IC. Here IB is not shown in the diagram. Somehow misprinting, right? So IB is flowing this and IC is flowing this. So basically it is IB is equal to minus IC, right? And as these two line connected, line to line fault, so IA is equal to 0. No fault, no current can flow through this because these two are short circuited. But this voltage is VA, this is VB, and this is VC, and this is the fault impedance ZF, right? So from your simple circuit analysis, you can find out VB minus VC will be ZF into IB. Right, and IB is equal to minus IC. IB direction we have taken downward, right? It is IB, and IB is equal to minus IC. It is downward, right? And the IC is entering, but it is a simple same circuit. So IB is equal to minus IC, right? So VB minus VC is equal to ZF into IB, and IB plus IC 0 means and IA 0. That is IB is equal to IC is equal to minus IB, or IB is equal to minus IC, right? This is the condition. Now we know same relationship IA1 IA2 IA0 is equal to one third of this matrix, then IB IA IB IC, right? So fault has a line to line fault, so IA is 0 and IB is equal to minus IC, or IC is equal to minus IB. So this is okay. So IA is 0, this is IB, IC is equal to minus IB, right? From which you will get, right? I mean, from this you will get it. You simplify a little bit, it will simplify a little bit, right? So IA0 is 0. You can find 1 into 0, 1 into IB minus 1 into IB. So it is IA0 is equal to 0. And if you solve IA1 and IA2, you will find IA2 is equal to minus IA1. You simply try to solve it, just multiply and see it, you will get it, right? Now, the symmetrical component of voltages under fault. So suppose phase A, VA1, VA2, VH is one third of this matrix into VA, VB, BC, right? Now, VA1, VA2, VA0, this is one third. This matrix, then VA will be there, VB will be there, and your VC will be from this equation that VB minus VC is equal to ZF IB. Therefore, VC will be VB minus ZF into IB, right? Therefore, it is VB minus ZF into IB. Now, if you multiply and find out, you will find 3 VA1 is equal to this equation, and 3 VA2 will be this equation. It is beta plus beta square VB. Here also beta plus beta square VB. This is minus beta square ZIF. This is minus beta ZIF. Right. Now, if you subtract this from 21, if you subtract equation 22 from 21, you will get 3 into VA1 minus V2 is equal to beta minus beta square is ZF into IB. We know beta is equal to e to the power j 120 degree. So according to that, you put it and simplify, you will get your 3 into VA minus V1, VA2 is equal to j root 3 ZF IB, right? Therefore, your IB, now your what you call that IB is equal to beta square minus beta your IA1. From this, your what you call this from the I mean whatever equations are given, you know that your IB is equal to IA1, your IA is equal to IA1, IA2, your plus IB0. So similarly, you know the your what you call expression of IB, I think beta square your IA1 plus beta IA2 plus your IA0, right? So accordingly, all these things you substitute. If you substitute, go back to the your previous chapter, right? And there you substitute, you will get IB is equal to beta square minus beta IA1. So IB is equal to minus j root 3 IA1. And this IB you substitute here. This IB you substitute here. If you substitute, it will be minus j square 3. J square is minus 1, so my plus. So it is 3 will be cancelled. Ultimately, VA1 minus VA2 will be ZF into IA1, right? Therefore, this is the relationship. Now you know positive sequence for and zero sequence current. Here it is 0, IA0 is 0. So no question of zero sequence diagram is required here. So only positive sequence and negative sequence, because this is the positive sequence voltage, negative sequence voltage, and zero sequence current IA0 is 0. So we are not bothering about that. So this is positive sequence, this is negative sequence. Now you have to connect according to the equation, you have to connect the circuit such that your VA1 minus VA2 should be ZF into I1. So accordingly it is connected. Look, here it is connected and here it is connected. And you have, if you apply KVL, it will be VA1 minus VA2 will be ZF into I1. So you have to, here opposite actually, positive, negative, zero sequence, all you are drawing. Here zero sequence is not required because zero sequence current is 0, right? So positive and negative sequence you are drawing. After that, to satisfy this equation, you have to draw this connection, right? Such that VA1 minus VA2 is ZF into your IA, right? IA1. So this is actually that from this equation, you have to connect it such that this equation holds, right? Otherwise, it is not correct. So this is the zero sequence diagram. From that, you can find out what is your I1 and IB is equal to minus IC. You can easily compute, right? This is your line to line fault, right? So you have to practice this because your test will be now offline, right? Now double line to ground fault. So in this case, what happened that this is your double line and line to line fault, then it is grounded to ZF, right? Anyway, if in this phase current is 0, IA0 is equal to 0, and this is Zn whatever it is coming here, right? So in this case, that IB this side and IB is side and this is going to the fault. So IB plus IC actually is the fault current, right? So both the current going to the fault. So whatever it is IC, whatever coming IB and going to the fault. So fault current will be your IB plus IC. Now in this case, IA is equal to 0. If IA is equal to 0 means IA positive sequence plus negative sequence plus zero sequence current is 0, right? Therefore, VB is equal to VC is equal to IB plus IC is equal, because if you look into the diagram that your this all are grounded. This is your what to call VB and this is VC, right? So here it is VB is equal to VC because this is also your these two are line to line fault to the ground, double line to ground fault, right? So VB and VC is same, right? Therefore, VB is equal to VC and fault current basically IB plus IC, whatever going to the fault. That's why it's equal to IB plus IC into ZF, right? Now, this is IB plus IC is equal to ZF, that is 3 ZF IA0. So, this one is a small exercise for you that I am writing ZF and IB plus IC, your whatever conditions is given. So, this is actually your what you call a small exercise for you, that you go to the previous equation, that previous chapter and try to do yourself, right? This is actually 3ZF IA0, right? And now symmetry, another thing I'll give you, that is a small exercise tool, because anyway now it is offline, so no open book, so you have to practice. Now VA, the symmetrical component of phase voltage, VA1, VA2, VA0, this much, this is VA, this is VB, and VC is equal to also VB, right? Therefore, VA1 is equal to VA2 is 1/3 VA plus beta square VB, right? Actually, previously we have seen beta square plus beta plus your 1 is equal to your what you call is equal to 0, right? So here also, if you simplify a little bit using those things, and you will find that VA1, VA2, later I will see that, and VA0 is 1/3 VA plus 2 VB. Now, if you subtract VA0 minus VA1, that is, this is VA0, this is VA1. If you subtract that VA1 from VA0, so VA0 minus VA1 is 1/3. 2 minus beta square VB, right? So just add 1 and subtract 1, right? Then beta square plus beta plus 1 is equal to 0. Previously we have seen. So ultimately it will become 3ZF IA0, right? Therefore VA0 is equal to VA1 plus 3ZF IA0. So this is positive sequence diagram. This is negative sequence diagram. This is zero sequence diagram. Now you have to connect these things such that and apply KVL such that this equation 35 holds, right? So from this equation you have to see the connection. So exam you have to, I mean very quickly you have to make it. So to making this is positive, negative and zero sequence. Look, this is actually, if you look into this, that this current, this, look at this condition, IA1 plus IA2 plus IA0 is equal to 0. Look, this current is IA1, this current is IA2, and this current taking this direction is IA0. At this point, if you apply KCL, IA1 plus IA2 plus IA0 is equal to 0. This condition holds, right? After that, VA0 is equal to V1 plus 3Z IA0. Look, this is connected here, and to make this and this is your, this connection and the all is made, right? And this is 3ZF. You see that the way connection has been made, that VA0 is VA0 holds. So from this equation only you have to see that how the connections are. Accordingly, looking at this equation, you have to make the connection, right? So this is actually this straightforward, but you should practice. You should practice. If little bit twisted this way, that way, then very quickly you have to make it. So from this circuit, if you solve, it is a basically series parallel circuit, right? So IA1 is equal to A upon this much, and IA2 will be this much. You can easily solve it now. You have done in circuit theory problem. So same way, your IA1, IA2 may be computed, right? And IA0 also can be computed. So this is actually line to line fault, line to ground fault, double line to line to line fault, line to ground fault, line to line fault, and double line to ground fault. These three are very important for this kind of your what you call for this kind of analysis. And looking at this equation or looking at the fault point, you have to connect the positive, negative, and zero sequence, because fault studies is one of the important topic in electrical engineering. When they make it, they first look into the fault things. If any fault happens, those things are not taught in your power system course. But if you those who are working in the power plant, right? So your what you call, and they are always alert about everything, right? And every time if you go to the control room in any power plant, you will see so many people, engineers, technicians, all are sitting and looking at all the meters, how things are varying, what changing, which side power is flowing, because they have to be alert all the time, right? And suppose several times this has happened, some grid outage, fault, right? Immediately you have to see whether your system is syncing or not. If you notice something, then you immediately have to disconnect your system from the rest of the system so that you will be saved, right? Otherwise a fault is or what you call, sometimes some fault is very quick, sometimes fault persists for a long time, slowly and slowly, right? So you will, if you go to the control room, you will find that people are always watching and observing everything, right? So nothing is easy actually. Power generation is that power system is the your largest man-made dynamic system on the earth, and it is a huge complicated system. It is not easy system. It is a huge complicated system, right? Right. So another thing is this, you can do yourself open conductor. Suppose one, this is open, this is A dash, this is B dash, this is right. So in this case, your VB dash is equal to VBB dash, VCC dash 0, because it is a continuous path. And in this case, line is cut. So IA is equal to 0. Accordingly, you have to draw this diagram. This is a simple thing. You can make it of your own, right? And suppose two conductors are open. So this way circuit is drawn. This way you will see this, right? So this is all for symmetrical component, right? So just see this one example. uh, just a single line diagram of the system is given. Just look at this example. So for the system shown in this example, the single line diagram is redrawn from figure 10.11, right? So the positive, negative, and zero sequence network of the system have already been drawn in figure this. Already it is there, right? Before the occurrence of a solid line to ground fault at line G, that is your here, the fault has occurred here at this point G. The motors were loaded. If the pre-fault current is neglected, even if it is not mentioned in the exam, you assume it is neglected. Calculate the fault current and substantial current in all parts of the system, right? So fault has occurred here. So how to do this? Suppose all parameters are given, right? Suppose these all parameters are given, how to compute? Another example will do, right? First you do positive sequence diagram. It is already given. This is negative sequence diagram. You make it, and this is zero sequence diagram. Already it is there, right? So now fault has occurred at this point ground. So this is you look into that at this point. Sorry, at this point G, right? A line to ground fault has occurred, right? So this is, if you see, this is your, you mark here, this is your G, because two after these two motors fault has occurred here to the your right to left, right? This is G. So first you mark here, it is G point, right here. So here also it is G point, right? And here also it is G point. Zero sequence diagram. Accordingly, first you draw this positive sequence, negative sequence, and zero sequence, and then this G point you connect to the ground. This G point, reference point rather, G point to the reference point, G to the reference point, and this reference point you connect to here, right? So when you solve the circuit, this is not coming, this is not coming, right? This part is not coming, this part is not coming, this part is also not coming. So ultimately, if you make an equivalent circuit, then you can easily solve this problem, right? And as I told that initially, all the voltages you will take one angle 0. So this is motor voltage, this is generator voltage, right? Accordingly, this has been solved. It has taken out, and finally you find out the equivalent impedance of all the things. If you take out these three are in you have to find out parallel, right? These two are in these two are in parallel, and then find out equivalent. And this is when you taking out also with parallel equivalent. With that, this is all these two sum and in parallel, because this point is here, right? And similarly here also, this is parallel, these two add in series in parallel, and here only this reactance, this is open, this is no need, because nowhere it is connected, right? Nowhere it is connected, so no need. It will be, even if anything is there, it will circulate inside. So nothing, no, not, here no question of circulation, right? And this is also open. If you solve it, then you will get all the your, what you call, all these things, right? So little bit I mean this per unit system and data, all these things will be shown, right? This I will take it in a next class, that how to solve all this problem. And here lot of computation will be there, and all this problem will be explained in the not today, in the next class. And how to draw everything, right? I will take one after another, and 3 4 I'll this thing, but before all I'll explain. But in this chapter you will do only two assignment I'll give. But note down, this all examples will be explained to you, right? Only two thing, and one, this 10.1 and 10.2, only two assignments will be given, not more than two. Last year I gave so many, right? But this time it is only 10.1 and 10.2, only these two as assignment. Now after this thing, tomorrow I'll not take any class tomorrow, but next Monday I'll take. After this, listen carefully, that after this, just hold on, right? I'm stopping sharing now. After this, your, what you call, two more chapters I'll cover, and I'll try to finish the course before 31st March. And when you will come to the campus, right? Today attendance is very poor. Like yesterday it was still 27, 28. Today is only 16. Anyway, so when you will be in campus, so yeah, I am going to the department in the morning hours, and now we have to go to this occasionally afternoon hours also, so, because the students are here, research students are here, right? You will meet me, and two more chapters. And before your arrival, I mean 31st March, before that many of you will arrive. And this course I'll try to finish by this time. I'm reducing one or two chapters. So after one or two chapters, I'll stop this thing. And I told the same thing, that your what you call that 30 marks for the offline test, 2 hours exam. And I told you this thing, but assignment you must submit. If anybody can submit all these assignment, then he or she will get full marks, right? And I'll tell you the deadline. But try to make everything. And today up to this, tomorrow I cannot take class, but Monday I'll take class. And another chapter, it will take 3-4 hours to finish. Another chapter also. So before your 31st March, I'll finish this thing. So thank you very much. And again, class will be on Monday. Thank you.